Today we will be looking at some real applications, engineering applications of programming, and we will see how whatever we have learned till now can be applied to solve some interesting problems like solving equations. One very common thing that uh, we need in any engineering or science is to represent data, right. One way of representing data is by in the form of a table, right. So, I can always represent some data as a table where there can be say on one column it may be height or depth, and maybe as we go down we bore through some point, and at different depths we find we put some sensor and get the temperature. So, that I can represent in the form of whatever is the depth 50 meters some temperature, 100 meters some temperature, etc. So, if we need to represent any data in this form, we know how to do it. We know that we can, as it looks here, we can immediately say okay, we will be representing it as array, whether I will be using using represent them using as one array, one 2-dimensional array or 2 different array will depend on the format of the data, the type of the data. For example, if the depth is integer and the temperature is real, then up to the knowledge that we have acquired till now, we will be representing them in the form of 2 arrays. One is an integer array, another is a separate floating point array, all right. So, that is one way, one aspect, one way of representing data, as we have done also in the case of students' roll number and marks earlier. Another very interesting thing and important thing is representing graphs. For example, I want to represent a graph like this. Say maybe this is say again some pressure, and this is depth. And as this graph shows that it is not increasing in a uniform way with depth, right. There could be some graph which would be just linear. This is, we call it linear, where along with depth this increases in a linear fashion. Here it is non-linear. Okay. So, the question is, how do we represent this sort of graph? Now, you know that this graph I can also state, if I say this is the x axis and my independent variable is x and the dependent variable is y, then this graph essentially represents a function which is y is a function of x. Now, depending on the nature of variation of the dependent variable with the independent variable, the nature of the function will vary. This one will be a linear function, right. For example, it can be here y equals to some k x, all right. This one is more complex. I could have had a quadratic function also. This is a linear function. Now, the question that we would like to first address is, it is so very nice to draw a picture on a piece of paper. However, a computer will not be able to just interpret this picture as we do. Then in that case, how do we represent this graph in a computer? So, let us do it again. So, I have got a graph, let us say a linear graph, and I can say that for different values of x, what is the corresponding value of y, all right. Now, this is a linear one. So, I can represent them, if x and y are of the same type, I can also represent them in the form of a table. That means a 2-dimensional array, where one side, one dimension is the variation of x. On one column we have got the x and the corresponding y, all right. And what will be the number of rows? The number of data points of x that we take will be the size of this array, not the size of this array, the number of rows, how many, n, and this one is fixed to be 2. I can suppose that this is 5.0 and this is 25. So, I have 5 here, I have 25 here. This array is of type float. Now, here it is 10, so it is 50, it may be 15, so this one will be 30, because I am talking of a linear curve. It need not be linear all the time. So, I can also have a curve like this. I can also have a curve like this, say something like this, and here again I have got the y and here I have got the x. So, with a particular value of x, say 5, maybe this one is initially, let us say it is it has risen a little sharp. So, maybe it is 7, and if I go here. Now, please note that we usually take the samples at equal distances. So, I take it as 10, but here it will not be double, it is becoming a little more than that. So, 7, it may be 16. I go here. Now, you see the slope of this curve has reduced, right, the gradient has reduced. So, at 15 it will not increase that much, it will be 18, say this is 18, because it is flattening out, still flattening out, and here there is a sharp change, etc. right. So, this one also I can represent in the form of a table, like say I have a 2-dimensional table where I have got 5, this is my x and this is my y. So, 5 corresponding to that 7, first row, that is the first point. I could have taken 0 0 also, that would be another one. So, 10 corresponding to that 16, then 15 corresponding to that 18. So, in that way it could go on. That means, whatever is this function f x, a function can be represented as an array, 2-dimensional array. Okay. So, that or as a table. So, this we have to remember either as one array or as two arrays, because if this was integer, this was float, then I would have needed 2 different arrays, right. It can be. So, here is a function. Now, let us look at another aspect. Sometimes some data I do not have the function, but I have got some data, right. So, here x and here is y, and I have got some data points for x equal to this is the y point, all right. So, if I call it x 0, this is y 0. Next one could be here that x 1, it is y 1. Here maybe it has come down, sorry, x 2 it is y 2, this will be y 2. So, I do not have a function right now, but I have got different data points and I have to find out the function. So, that is also another very interesting thing, finding out the function that can represent this distribution of data points. Might be here again there is x 3 and it is again gone up here. So, it is not a straight line. If I want to fit a curve to meet that, how would that curve look like? The curve will be something like this, right, and I have to find out what function is this curve, what is the function? I do not know as yet. That is another challenging point, all right. So, first of all, graphs or data points, graphs can be represented as table and the distribution of data points can also be represented as table, because here in this scenario I do not have a function, but certainly I have got the x and y values known to me. Therefore, I can represent that as a table. Another point to note here is that usually this independent variable, the sampling points that I am taking are usually equidistant. So, I can say x 1 minus x 0 is some value h, x 2 minus x 1 will be the same h. Usually we represent that in order to see for an incremental fixed incremental increase of the independent variable, how much does the dependent variable vary. Okay. So, I can say in general x I plus 1 minus x I is equal to h, right. So, this is typically how we write. Now, we have got a number of problems to solve using data. So, for example, let us start with one problem, finding the root of a function. Finding the root of a function. Some function f x. Now, finding the root means essentially it is solving the equation. So, if I have got a function f x, then my equation is f x equals 0 and I want to solve this, right, and I want to find out the root, at least one root. Now, what do I mean by the root? The root is that if there is a function like this, say there is a function like this. So, for what value of x, f x equal to 0 is the equation. So, this one is f x, y or f x. So, we have to find out for what value of x, for which value of x, f x is 0. So, that is the root. Now, this particular function, if this be an f x, then it has got two distinct roots, right. Another function could be something like this, could be just like this, where I have got one root. This is the point where f x equal to 0, all right. So, one of the major problems is finding out the root of a function, or we will say in general the root of a polynomial. Why are we saying a polynomial? Because you know that any function, say f x is equal to 3 x square plus 2 x plus 3 is a polynomial of degree 2, right, or this f 1 x. I could have another f 2 x as 4 x. This is a polynomial of 4 x plus 3 maybe, all right. Now, anybody who remembers school coordinate geometry, this is a linear equation because it is a polynomial of degree 1. That means, if we say this to be y, then this is y equals m x plus c. So, m, this 4 is nothing but the slope of this straight line. So, there will be some slope of this straight line, this is linear, all right. This one is not linear, this is quadratic. Okay. So, I can have the different functions can be written as a polynomial, and when the polynomial is equated to 0, it becomes an equation and we want to solve that equation. Problem number 2 is interpolating a function. I will describe what interpolation is a little later. Okay. But before that, let us try to see a very simple way of finding the root of a function. Say I have got a function x and y, all right, and a function is something like this. Now, I want to find out this point, what is the value of x, this value, okay, for which this y is 0. Now, the method that we will be talking about is known as the bisection method. This is a very common and interesting approach. You have seen in binary search also, we have partitioned the array into two halves and then went to one half. Very similar to that, let us see how the bisection method tries to find out the root. First, we start finding two arbitrary points, say x 0 and x 1, such that f x 0 and f x 1 are of different signs. So, here you can see this is plus, this is minus, right. F x 1 is the y value corresponding to x 1. So, if the y value of x 0 and x 1 are opposite, then it is immediately understood that the root must lie somewhere in between. Okay. So, we will then try to find out the midpoint of x 0 and x 1. Suppose the midpoint of x 0 and x 1 is x 2. So, if x 2, f x 2 and f x 0 are of opposite sign, then I will again find then the root must be I have reduced my space, right. So, it is between x 2 and x 0. So, I again find out the value, the midpoint of x 2 and x 0. Suppose that midpoint is here, suppose this is x 3, and these two f x 3 and f x 2 are of opposite signs. Therefore, I will find the midpoint of these two. So, suppose the midpoint of these two is this x 4 here. Now, still this one and this one are of opposite sides. Therefore, I will try to find out the midpoint of these two. So, I will come somewhere here, all right. In that way we approach till what? Till we find that the value of y is very close to 0. The value of y is very close to 0, very close to 0. Why am I saying very close to 0, not exactly 0? There are reasons for that. The reasons we are coming to that. A computer works with finite representation of numbers. So, we may not get exact 0, but suppose I get this, and then I can assume that to be 0, because it is very small, and often we call it that the difference, that the value of f x at that point is less than equal to some very small value epsilon that will decide a priori. Okay. So, however, so you have seen this approach. Now, one thing that you can quickly think of, that how would I know that these two are of opposite signs, f x 1 and f x 0 are of opposite signs? If I take the product of this, then obviously if they are of opposite signs, the product will be negative, that is less than 0. So, at every point we check whether they are less than 0. If there is no root, suppose it goes like this, then I will not find any point where they are of opposite signs. Okay. So, that is the basic idea of bisection method. Now, when I carry it out through a computer, such attempts to solve such problems are known as programming numerical methods. And we will start with some representative relatively easy one, examples of those, some numerical methods. One of them is finding the root of a function, root of a polynomial. Okay. Now, while doing these numerical methods, we always encounter errors, okay, and our algorithm will be better if the error is less. Now, what do I mean by error? Say I am computing 4 by 3, all right. What is the result? Result is 1 point, correct result, most accurate, absolutely correct result. Do you know that? No, 1.3333, it goes on. Now, how much my computer, you know, our computers have got some storage locations of some 8 by 8 bits or 16 bits like that. So, depending on that, I have got a finite capacity to store the data. Therefore, I may represent this as say 1.3333. I just start with say 6 digits, all right, 6, 7, 8. I can store 8 digits maximum, 6 after decimal, 1 decimal and this. So, 6 places. Therefore, I am actual thing was much more. So, I am encountering, I am actually committing some error. So, what is the error? Error in computation is the exact value, the difference of the exact value by this and the computed value. It can be positive or negative. All right. Suppose the result is actually 1.523, that is the exact value, suppose, and during my computation I got 1.52283. Okay. Then the error is the difference between these two, and the error is therefore, if I subtract this, it will be 0.0000177, that is the error. Now, the smaller this error is, more accurate my result is. I think it is very clear. Now, there are two types of errors also. One is a round off error. For example, here I could have rounded it off as 1.522, 1.523. So, suppose the actual thing was this and I rounded it to 1.52 by approximating, if I go by 2 bits. That is one type of error. Other type of error is truncation error. This was there, I have just dropped this 1.52 because I could not store more. So, there are two types of errors, right. So, truncation error and round off error. Another term that you need to know is the absolute error. Absolute error is nothing but the absolute value of the error, okay. And relative error is absolute error divided by exact value, the absolute of the exact value. All right. Absolute error is the error's absolute part and by the exact value, and percentage error will be relative error times 1000. Okay. Relative error times 1000. So, we can say that percentage error is relative error into into 100, what am I saying. So, now just look at this, have a quick look at these definitions. Absolute error means the absolute value of the error, relative error is absolute error divided by the exact value, and then we come to the percentage error, which is relative error times 100. Okay. Now, another important thing that we have to consider is accumulated error, but that we will consider later. Next, in the next lecture we will move. So, whatever we do, the way we do the computation, we must be very careful about the algorithm be such that it does not accommodate too much error. However, discussing about error analysis in general is beyond the scope of this course right now. So, we will in the next lecture start with the bisection method as I have explained, and then move to some other methods.